The smallest unit of memory is a binary digit, also called a bit, which can hold a value of 0 or 1. You can think of a bit as being like a traditional light switch. Either the light is off 0, or it is on 1. There is no in between. If you were to look at a random segment of memory, all you would see is 0, 1 or some combination thereof. Memory is organized into sequential units called memory addresses, or addresses for short. Similar to how a street address can be used to find a given house on a street, the memory address allows us to find and access the contents of memory at a particular location. The following picture shows some sequential memory addresses, along with the corresponding byte of data. Because all data on a computer is just a sequence of bits, we use the data type, often called a type for short, to tell the compiler how to interpret the contents of memory in some meaningful way. You have already seen one example of a data type, the integer. When we declare a variable as an integer, we are telling the compiler the piece of memory that this variable uses is going to be interpreted as an integer value. When you give an object a value, the compiler and compu take care of encoding your value into the appropriate sequence of bits for that data type, which are then stored in memory. Remember, memory can only store bits. For example, if you assign an integer object the value 65, that value is converted to the sequence of bits 01000001 and stored in the memory assigned to the object. Memory of modern machines is typically organized into byte-sized units, with each byte of memory having a unique address. Up to this point, it has been useful to think of memory as a bunch of cubbyholes or mailboxes where we can put and retrieve information, and variables as names for accessing those cubbyholes or mailboxes. However, this analogy is not quite correct in one regard. Most objects actually take up more than one byte of memory. A single object may use 2, 4, 8, or even more consecutive memory addresses. The amount of memory that an object uses is based on its data type. Because we typically access memory through variable names and not directly via memory addresses, the compiler is able to hide the details of how many bytes a given object uses from us. When we access some variable x, the compiler knows how many bytes of data to retrieve based on the type of variable x, and can handle that task for us. A single bit can hold two possible values, a 0 or a 1. 2 bits can hold 4 possible values. 3 bits can hold 8 possible values. To generalize, an object with n bits can hold 2n, 2 to the power of n, also commonly written 2 circumflex n, unique values. Therefore, with an 8-bit byte, a byte-sized object can hold 28,256 different values. An object that uses 2 bytes can hold 2 circumflex 65,536 different values. Thus, the size of the object puts a limit on the amount of unique values it can store. Objects that utilize more bytes can store a larger number of unique values. We will explore this further when we talk more about integers. The obvious next question is, how much memory do variables of different data types take? You may be surprised to find that the size of a given data type is dependent on the compiler and all the computer architecture. In order to determine the size of data types on a particular machine, C++ provides an operator named sizeof. The sizeof operator is a runary operator that takes either a type or a variable, and returns its size in bytes. You can compile and run the following program to find out how large some of your data types are. An integer is an integral type that can represent positive and negative whole numbers, including 0, for example -2, -1, 0, 1, 2. C++ has 4 different fundamental integer types available for use: The key difference between the various integer types is that they have varying sizes. The larger integers can hold bigger numbers. When writing negative numbers in everyday life, we use a negative sign. For example, -3 means -3. We also typically recognize +3 as +3, though common convention dictates that we typically omit plus prefixes. This attribute of being positive, negative, or 0 is called the number's sign. By default, integers are signed, which means the number's sign is preserved. Therefore, a signed integer can hold both positive and negative numbers and 0. Here is the preferred way to define the four types of signed integers. Short s, int I, long k, long w. Unsigned integers are integers that can only hold non-negative whole numbers. To define an unsigned integer, we use the unsigned keyword. By convention, this is placed before the type. Unsigned short s, unsigned int I, unsigned long I, unsigned long I. A 1-byte unsigned integer has a range of 0 to 255. Compare this to the 1-byte signed integer range of -128 to 127. Both can store 256 different values, but signed integers use half of their range for negative numbers, whereas unsigned integers can store positive numbers that are twice as large. Integers are great for counting whole numbers, but sometimes we need to store very large numbers, or numbers with a fractional component. A floating point type variable is a variable that can hold a real number, such as 4320.0, -3.33, or 0.01226. The floating part of the name floating point refers to the fact that the decimal point can float. That is, it can support a variable number of digits before and after the decimal point. There are three different floating point data types: float, double, and long double. As with integers, C++ does not define the actual size of these types, but it does guarantee minimum sizes. On modern architectures, floating point representation almost always follows IE 754 binary format. In this format, a float is 4 bytes, a double is 8, and a long double can be equivalent to a double, 8 bytes, 80 bits, often padded to 12 bytes, or 16 bytes. Here are some definitions of floating point numbers. Float value, doubled value, long doubled value, int x 5. 5 means integer. Double y 5.0. 5.0 is a floating point literal. No suffix means double type by default. Float z 5.0 f. 5.0 is a floating point literal. F suffix means float type. There are two special categories of floating point numbers. The first is inf, which represents infinity. Inf can be positive or negative. The second is nan, which stands for not a number. There are several different kinds of nan which we won't discuss here. Double 0, 0.0. Double posinf 5.00. Positive infinity. STD, caught less than posinf less than STD. Endl. Double neginf -5.00, negative infinity. STD, caught less than neginf less than STD, Endl. Double nan 00, not a number, mathematically invalid. STD, caught less than nan less than STD, Endl. These kinds of sentences that have only two possible outcomes, yes true, or no false, are so common that many programming languages include a special type for dealing with them. That type is called a Boolean type. Note, Boolean is properly capitalized in the English language because it's named after its inventor, George Boole. Boolean variables are variables that can have only two possible values, true and false. To declare a Boolean variable, we use the keyword bool. Bool b1 true. Bool b2 false. B1 equals false. Just as the unary minus operator dash can be used to make an integer negative, the logical not operator can be used to flip a Boolean value from true to false, or false to true. Bool b1, true. b1 will be initialized with the value false. Bool b2, false. b2 will be initialized with the value true. Boolean values are not actually stored in Boolean variables as the words true or false. Instead, they are stored as integers. True becomes the integer 1, and false becomes the integer 0. Similarly, when Boolean values are evaluated, they don't actually evaluate to true or false. They evaluate to the integers 0, false, or 1, true. Because Booleans actually store integers, they are considered an integral type. Hash sign include int main, std, caught less than true less than std, endl. True evaluates to 1. std, caught less than true less than std, endl. True evaluates to 0. Bool b, false. std, caught less than b less than std, endl. b is false, which evaluates to 0. std, caught less than b less than std, endl. b is true, which evaluates to 1. Return 0. Hash sign include int main, std, caught std, bool alpha, print bools as true or false. Bool b1 equals 4. Copy initialization allows implicit conversion from int to bool. std, caught b1 backslash n single quote. Bool b2 equals 0. Copy initialization allows implicit conversion from int to bool. std, caught b2 backslash n single quote. Return 0. Closing brace.
The char data type is an integral type, meaning the underlying value is stored as an integer, and it's guaranteed to be 1 byte in size. However, similar to how a Boolean value is interpreted as true or false, a char value is interpreted as an ASCII character. ASCII stands for American Standard Code for Information Interchange. And it defines a particular way to represent English characters, plus a few other symbols, as numbers between 0 and 127, called an ASCII code or code point. For example, ASCII code 97 is interpreted as the character A. Char ch2 A, initialize with code point for A, stored as integer 97, preferred. Char ch197, initialize with integer 97, not preferred. Be careful not to mix up character numbers with integer numbers. The following two initializations are not the same. Char ch5, initialize with integer 5, stored as integer 5. Char ch5, initialize with code point 45, stored as integer 53. When using stdcode to print a char, stdcode outputs the char variable as an ASCII character. Hashtag include int main. Char ch1 preferred. stdcode ch1, code prints a character. Char ch298, code point 4b, not preferred. stdcode ch2, code prints a character. Return 0. Hashtag include int main. stdcode input a keyboard character, assume the user enters ABCD, without quotes. Char ch. stdcinch, ch equals a, BCD is left queued. stdcode ch has ASCII code static cast, ch. Note, the following cin doesn't ask the user for input, it grabs queued input. stdcinch, ch equals b, cd is left queued. stdcode ch has ASCII code static cast, ch. Return 0.